Alright, this is part 3 of transregion method using dog-leg approach. We talked about how we can basically solve the solution using transregion dog-leg method. We talked about toward the end that the direction can be a combination of Newton's direction and steepest descent direction depending on the size of these directions. Okay, so in the MATLAB script we were talking about how we can combine the two directions, the steepest descent direction and the Newton's direction. To do the combination, we have to first calculate the steepest descent direction. Then we find the solution if the steepest descent direction is the direction to follow. We also find the Newton's direction and the solution from the Newton's direction. Okay, now we have to choose which one of these will be the next step. We're going to compare the length or the norm of the Newton's direction. If that norm is less than or equal to our threshold delta, then we're going to keep Newton's method. Otherwise, we're going to check if the norm of the steepest descent direction is bigger than delta, then we're going to keep the steepest descent direction using steepest descent method. If none of these happens, then it has to be a combination of Newton's solution and steepest descent solution using the lambda. And we have the equation for lambda using the lecture note here. So we find the lambda from here and then use it to calculate the next step. And that's what we have here. So here is the lambda, which is a combination of the norm of the steepest descent direction and the norm of Newton minus steepest descent direction. Once we find lambda, we can update the x. So at the end of the day, we have the x, which is coming either from Newton solution, steepest descent solution, or a combination of both. Well, as soon as we have the new solution, we can get the direction, which is the difference between the solution minus, the next solution minus the current solution. So that's going to be the p. And then we can calculate the ratio. Okay, so the ratio is how much we're making progress comparing the function, the real function, and the Taylor series version of the function. And remember, this m actually is coming from our definition of here. So we define the first three terms of the Taylor series using the function, the gradient, and the change in the x, which is p, or the direction. Right, so all of these are lumped into this function m, which is function of x and p. And this time, I'm just calling the function using the solution and the direction. So initial direction is 0. Now is direction p. So we're going to measure how much we changed, the Taylor series version. And here is how much we change the f by going from x to x plus p. Right, from x to x plus p. Okay, now we have the row. We can basically decide if we want to change the delta. So if a row is less than eta 1, it's basically right here. If a row is less than eta 1, then we have to decrease the delta. So we're going to decrease it by a factor of t1. And t1, if you remember, initially was set to 0.25. And that's exactly 0.25 here. If a row is bigger than eta 2, it's going to be double the current delta. And so down here, so if a row bigger than eta, then we're going to double it. So this is t2, which is 2 times delta. And we also have to bound it by the maximum delta. Okay, so just to make sure t2 is 2, right? Now, so we talk about eta 1, we talk about eta 2. And the last option is if none of these happens, then we're not going to change delta. So in the script, we don't do anything. I mean, if none of these happens, we just keep delta. This is just to plot the current solution. And so this is to plot actually the next solution. This is to plot the current solution. And this is just a print command to look at the iteration number, the solution, the direction, the delta if it has changed, the ratio of the change in the function, and the Taylor series version and lambda. So I'm going to print out all of them as a table here. And that is it. So there's one part that I skipped, and that's this one. This is just to plot, the truss region. So at every step at center X, I'm going to plot a circle with radius delta to just show, how delta is changing. This is just for visual representation of dogleg method. Is nothing really serious or nothing really necessary for dogleg method. If you just comment this out, nothing happens. It's just all plot functions. And in here, what I'm saying is that if norm of the steepest descent direction is less than delta, and norm of Newton's direction is bigger than delta, and the ratio is bigger than 801, then we plot the solution from steepest descent direction, and yeah, so right. So this is basically to plot the trajectory of how dogleg method is converging to the solution. So once I do that, you see what I mean by this. Okay, let me just continue running the code. Let me just make sure that didn't stop somewhere. No, I think I got the solution. So let's look at that. In 8 iterations, we get the solution. This is, okay, first we see how X is progressing. This is the direction, this is the delta. You see that sometimes actually delta is going up. So initially we start from 0.1, 0.5, 0.5, 0.5, and then at this point we found that actually the step size can be increased to 1. So we double the step size, and we even make it double next time step. And these are the lambdas. This is the rho, which is the ratio of the change in the function divided by the change in the Taylor series version of the function. Okay, I also have a plot for it. And so these are the circles that I was talking about. So initially we start from this point. This is the truss region. That means our step size cannot go beyond this. And so we're going to go along, different directions, I think. This table doesn't say whether that's the steepest descent direction or Newton's direction, but anyways, I believe the red is the steepest descent direction. I'll make it bigger. I guess the red is the steepest descent, and the black is, you see that actually we are not going along the red direction. So red is kind of zigzag, but then black is, it's more efficient. So like instead of 2 steps here, we just do 1 step, like another 2 steps in, a zigzag pattern of steepest descent, we just do 1 step. So now this is a bit more efficient. So anyways, up to here, you see that step size is almost the same. So these circles have the same radii. Now from this step to that step, the step size actually goes up by a factor of 2. Now you see that the size of this circle is twice the size of that. So from here to here, we see that actually we can go even faster, and we increase the step size by a factor of 2. Now, from actually here to here, the step size even got bigger. So now you see that the step size in this step, which is the radius of this circle, is twice the radius of this circle. So now that's actually make the convergence even faster. So from here to here, we made even faster. And then from here to here to here, we have the same step size. So you see that we can basically tune the step size as we get closer to the local minimum. Alright. So that was trust region using dogleg method. I hope this is useful. Let me just make sure that I didn't miss anything. And this is the function that I use to draw the circles. I think there's nothing special about it. I use, like 50 points along a circle. We make some, points along the boundary of a circle, and we just connect them together using the plot command. So we get a circle. There's nothing actually special about this plotting circle. Anyways, so I hope this is useful. Thanks all for watching. Stay tuned for the next video on nonlinear optimization.